Okay, we can go.
We were talking about a new state of conduction electrons in the metal, which corresponds to a spin density wave, where the upspins and downspins both undergo a sinusoidal modulation in density as a function of position in some direction. And shown here is a spin density wave, because here the upspins predominate and here the downspins predominate. So it goes from up, down. And I gave the name of that new state of electrons in metals a spin density wave. Such a state was actually first found in the pure metal chromium, which of course you all know what chromium looks like, very shiny, bright metallic sheen. If you move one of these spin densities half a wavelength to the right or left, then the upspin and downspin peaks are on top of one another, and so when you add up the total density, you just get a constant independent of position. You know, if you add up the spin densities, you get a constant because the upspins cancel out the downspins peaks. But you end up with a net. You add the two densities together, since the peaks are on top of one another, the valleys are on top of one another, one ends up with a charge density which is modulated sinusoidally as a function of position. And this I gave the name a charge density wave. So that's a new possible state of matter, and that state of matter does appear to exist in the alkali metals, lithium, sodium, potassium, rubidium, and cesium. They're all metals in which there is one conduction electron per atom. The simplest metal is potassium because it doesn't undergo crystallographic changes when you cool it to low temperatures, which is necessary for many experiments that you wish to do on metals, so that at very low temperatures the electrons travel long distances without being scattered. Over the last years, since 1963, there have been 30 different anomalous phenomena observed experimentally in potassium metal. And what's interesting about all these observed phenomena is they cannot be explained by just taking it for granted that the electron density is a constant as a function of position. But if you put the charge density wave modulation in, which I talked about a few minutes ago, then all of these phenomena, there are 30 of them listed here, can be explained. And many of these phenomena are really quite spectacular. And over a 40-year period, I wrote about 65 research publications explaining all of these phenomena. And so, you know, some discoveries take only 2 hours. The idea behind that gravity experiment I mentioned to you took me only 2 hours to come up with. But my work on potassium metal, the electronic properties of potassium, has preoccupied me for more than 40 years. And in order that this work will become perennial, I'm in the process of putting together a book on the subject, which may or may not be published. Maybe too long for a good publishing house to take it on. But intellectually, this is the most important work of my life. As I say, I've written essentially 65 research papers that are relevant to the anomalous properties of potassium metal. I believe that the other alkali metals, the four other ones, lithium, sodium, rubidium, and cesium, also have charge density wave structure, but for one reason or another, they are not as useful as far as doing important experiments, because they undergo changes when you cool them down to almost absolute zero, where you want to still have a nice, beautiful single crystal. But that you can do usually for potassium, but not for lithium or sodium. And rubidium and cesium are very hard to work with. Cesium will essentially spontaneously ignite in air. And it's very soft like butter, so it's hard to have a nice single crystal, which you need for doing many of these experiments.
What about the National Medal of Science?
Well, in 1994, I received the National Medal of Science from President Clinton. There it is. But I guess it was given for my contributions to the work I've done on metals. One thing that one's peers always like to do is to look up the number of citations you have for various research papers. Excuse me. The work of mine which has the most citations was work on lattice dynamics. Usually you think of an atom as just some round little spherical ball, and when the atoms vibrate, they vibrate as a whole. In other words, the whole atom goes back and forth during a vibration inside the metal crystal. But I invented another model called the shell model, in which the inner part of the ion is one thing, and then the outermost part of the ion is a shell of electrons. So while the atom is trying to vibrate, the inner ion core is vibrating also relative to the outer shell. So this became known as the shell model, and it really contributed a lot to our understanding of vibrations of atoms in crystal solids. That particular paper introducing the shell model is the paper of mine with the greatest number of citations. The last time I looked, there was 1,637 citations to that paper. It isn't all that important, but it has been cited many times. My work on the dynamic nuclear polarization only has about half that many citations, but it's far more important, of course.
If you were a subatomic particle, which one would you be, and why?
I've never thought about being a subatomic particle. I guess the smartest thing to say would I would like to be a neutrino. Neutrinos have no charge, no magnetic moment, and they travel through the entire thickness of the Earth without being scattered or absorbed. They're very puzzling particles.
Newton or Einstein?
Pardon me?
Newton or Einstein?
What about them?
Which one?
Which one what?
Which one do you prefer?
Oh. It's hard to say. They both played an important role in the development of theoretical physics. I don't wish to indicate a preference for one or the other.
If you were the president and had the power to repeal one law of physics, which law would you repeal?
Which law would I repeal of physics? Well, if you repeal any of the laws, we would cease to exist, so I reject the question.
Okay.
I mean, even if you just change the value of a fundamental constant by a little bit, you change the value of the charge on an electron by a few percent, then all of the things that led to the formation of the universe as we know would no longer work. So the universe has been put together with immaculate care. And it's what's really a mystery is why the universe exists at all. We like to think of empty space is where we occasionally find a star or black hole or a planet or a meteor, but nobody knows where space comes from. It's not susceptible to a scientific investigation, because you can't do an experiment where space is absent.
Okay, that's all the questions I have.
Where were you when you found out you were getting the National Medal of Science? And what did you do?
Well, I'd been somewhere. I don't know whether I'd been on vacation or I'd been away to give a talk somewhere. But I came home and I had a telephone message to call somebody. I forget his name now, but he was... I think he had an office in the White House, but I didn't recognize his name. And I assumed to start with that he just probably was going to ask me to serve on some committee. The last thing I like to do is serve on committees. And so I decided I'm just going to ignore the telephone message. But after an hour or two, I got a bad conscience and said it's not polite to not return a call. So I returned the call to this person, and he was the White House science advisor, and his call had been to notify me that I was going to be awarded the National Medal of Science. So that's how I found out about it. I'm glad I returned the call.
So what did you do when you found out?
Well, there's nothing to do there other than make travel plans so I could go to Washington, D.C. on the appropriate day. And I guess several members of my family came along. Did you come for that?
Yeah.
And of course, Margaret came.
So did William, though he was only 1 year old at the time. So what was the award ceremony like?
What was the awards ceremony?
When you got the medal, what was it like?
I don't know. I mean, I don't remember. Somebody, the president couldn't come for some reason or other, so the vice president made the presentation, and he just read something that somebody had obviously written for him, and probably some auditory message of some sort of thing having to do with theoretical physics, I guess. I don't know who nominated me for the National Medal of Science.
Are there any other scientific awards you've gotten?
Yes. I won the Oliver Buckley Prize awarded by the American Physical Society for my research in condensed matter physics, physics of solids. I've been elected a member of the National Academy of Science, and I've been elected a fellow of the American Academy of Arts and Sciences. Last year I received the Russell Varian Prize awarded by the European Society for Magnetic Resonance. And I've won 3 honorary degrees, one from the University of Chicago, one from Simon Fraser University in Canada, and I won an honorary degree also after retirement from Purdue University.
Can you describe what this is? And
This is the original Western Union telegram that I received in August 1953, a few days after our family moved to Ithaca, New York, where I became an assistant professor of physics. And the secretary left a note on my office door saying I had a telegram, which made me fearful immediately, because in the 1950s one usually got telegrams only to tell you that some member of your family had died. But after thinking about it for a couple hours, I decided to go pick up the telegram, and fortunately it was something joyful rather than something tragic. This was a telegram from Charlie Slichter, who was the professor at University of Illinois in Urbana, who was doing the experiment on dynamic nuclear polarization. And he says in this telegram that he was able to polarize the nuclear spins of lithium metal using what later became known as the Overhauser effect. The very first time they tried the experiment, it was a complete success. And so that's the original telegram.
so what did you do after you got the telegram?
We were looking for a house to buy for our family, which didn't exist yet. I mean, your older sister hadn't been born yet, but was due any day. So we continued looking for a house to buy in Ithaca, New York.
When did the name Overhauser effect start getting used?
I have no idea.
Was it like many years after the original experiment?
I think it was sooner than that, but I don't know who started that. I didn't keep up with the applications to chemistry. There was somewhere, was that the article, the letter from Switzer that you have there?
Oh, let me find it.
I just don't want to lose it.
Yeah, it's here.
Well,
You want to describe what these are?
well, this is a letter from Charlie Switzer that came after the telegram, giving me more details of the experiment that they did. And this is a Polaroid picture. Here is the nuclear resonance of lithium metal without the microwaves turned on, which would hit the electron spin resonance. there's nothing there. There's presumably a tiny resonance signal here, but it's too small to be seen. And then when you turn on the microwaves to hit the electron spin resonance, you suddenly get a very nice nuclear spin resonance as shown here. And since the experimental sensitivity was measured quantitatively before this experiment was done, they were able to decide that this resonance was 100 times larger than what it is in this line here. 100 times smaller than that would not show up at all. But the factor of 100 was what was predicted for the intensity of microwaves that they had available to them. So I believe that this polarized picture of the actual resonance probably came to me with this letter.
Okay. Did you meet all your requirements for graduating from high school?
For graduating from high school, I did, yes.
Even PE?
No, you're referring to junior high school.
Oh.
I didn't meet my requirements for graduating from junior high school, that is from 9th grade, because I didn't have enough courses, sufficient courses in physical education. And I was practicing with the orchestra for the graduation seminar, and the principal of the school came by and sat down next to me and leaned over and took my report card off my music stand and looked at it and says, "You're not eligible to graduate because you haven't had the required number of physical education courses." And I didn't know what to do about it, so he picked out his pen and filled in some blank spaces on that could hold another physical education course. Then he asked me, "What teacher would you like to have had?" And so he forged that teacher's name to my report card, which made me eligible to graduate from junior high school.
Okay. Can you describe what that gizmo is over there?
What,
And the,
this?
yeah.
Well, this piece of apparatus here is called a goniometer. It's used to hold, here is a sample. This sample here is a sample of, a single crystal sample of potassium metal. And of course it looks real nice and shiny because potassium is a good metal. And this goniometer is used to orient this crystal sample appropriately, so when X-ray beams or neutron beams come in, they will be reflected off the planes, the atomic planes. And so the orientation, there's an arc that bends this way and there's an arc that bends that way. And by carefully adjusting those two arcs, you can get the atomic planes that you wish to reflect your X-ray or neutron beam to be the correct orientation for reflection. So the beam comes in this way and then goes out in another direction, also in the horizontal plane. So this sample was made, grown in this Pyrex tube back around 1972, so it's close to 40 years old, but I'm sure it's still a perfect single crystal.
How many different experiments have you used that in?
Well, that sample has been cooled to near absolute zero, probably 20 or 30 times. shows no deterioration from.
So,
We haven't looked at it in quite a few years now.
what's the significance of the red glasses there on your desk?
That's just a spoof. When I discovered that all metals could be eligible for having a spin density wave, broken symmetry, as I tried to describe half hour ago, people would sometimes say that I look at the world through spin density wave glasses, that no matter what I look at, I will find a spin density wave. So they make fun of me that way. So the best way to beat them in making fun of you is to make fun of yourself. So I took these old pair of glasses and cut out some sticky paper with the SDW, admitting that when I look at metals, I tend to see spin density waves.
Can you put them on?
Well, they'll probably still fit. Well, right now they don't go behind my ears. But that's sufficient, I think, right? If I were to make these glasses now, I'd have spin density wave in one eye and charge density wave on the other eye. The charge density wave is more prevalent than spin density waves.
So what other things that you haven't mentioned do you want people to know about you?
Well, I don't think about questions like that.
Are there any other scientific ideas that you have that should be mentioned?
Well, I'm sure there are, but I can't think of any right now.
Okay. Well then, that concludes our interview for today. Thank you for your time.
You're welcome.